bit of material that I still want to do, and that's Descartes' law of sums. And Descartes' law, so what tricks do we have right now? We have this trick about polynomial division. Once you find a zero polynomial, you can do polynomial division to simplify the polynomial. Once you find, so how do you find factors? Well, one way of finding candidates to be zeros of the polynomial to get this algorithm started is the rational roots test, which gives you this finite collection of numbers which will contain all of the possible rational solutions to a polynomial equation. Wow. And between those two things, you can get a lot done. This Descartes' law of science is going to tell us something else. It's going to tell us something about how many solutions to expect. In particular, how many positive and negative solutions to expect. So here's what it says. Let P of x be a polynomial written with the powers of x in descending order. So if someone gives you a polynomial in the form x to the fifth minus x plus x to the fourth plus 1, you have to put the coefficients in order before you can use this. Then the number of positive solutions to P of x equals 0 is equal to either the number of times the sign of the coefficient changes from positive to negative or negative to positive, or that number minus an even integer. So let's run this for an example. So here's a polynomial. It's degree 4, so I know it might have up to 4 solutions. Let's apply Descartes' law of sines, which says something about how many times the coefficients change from positive to negative. From 4 to negative 2, did the coefficient change sign? From negative 2 to 1, did the coefficient change sign? From 1 to 1, did the coefficient change sign? So how many sign changes were there? 2. 2 sign changes. Namely, that sign change and that sign change. So that tells me that there will be 2 or 0 positive solutions. That's all Descartes' law of sines says. But you can be clever with Descartes' law of sines and realize that you can get it to tell you something about how many negative solutions. Because what can you do? You can say, well, the number of negative solutions should be the same as the number of positive solutions to P of negative x equals 0. So if something is a positive solution to Q of negative x equals 0, then negative, that solution is a negative solution to P of x equals 0. So let's count how many negative solutions this thing might have. So let's compute P of negative x. So that'll be, I'll do it in maybe more steps than you would. 4 times negative x to the 4th plus 2 times negative x squared plus negative x. Hope that should be a minus sign. Plus 1. And now we expand. Does a negative sign matter if it's inside of a thing to the power of 4? No. So that'll give me a 4x to the 4th minus, that negative sign doesn't matter, so minus 2x squared. That negative sign does matter, minus x plus 1. So, same question. Looking at that, how many times does it change sign? Twice. 2 sign changes. So that tells me there will be 2 or 0 negative solutions. That will make sense? I mean, I haven't given you a reason to believe it, but what it says makes sense? Nice. So the only other thing that I wanted to do in this packet, and if the previous section is a model to follow, this will take the remaining time, is I'm going to go through one example of using all of the tricks we've developed to solve some polynomial equations, to solve one polynomial equation. And then I'll have you guys do the same. Use the sum total of all of these tricks to solve a polynomial equation. So let's do it. So, altogether, let's find the solutions to x to the 5th minus 7x to the 4th plus 19x cubed minus 47x squared plus 60x minus 46 is equal to 0. So first question, what's the degree of this polynomial? 5. 5. So how many roots might there be? Even if we count them with multiplicity. Let's decide how many of these roots should be positive, how many should be negative. Descartes' rule of signs won't be able to tell us anything about complex solutions. That we just have to accept that Descartes' law of signs won't see at all. Let's count them up. So looking at the formula for p of x, how many sign changes do you see? 5. So how many positive solutions might there be? 5 or 3 or 1. 5 minus an even number. So there could be 5 or 3 or 1 positive solution. I guess one thing that's noteworthy is Descartes' law of signs is definitely telling us, without a doubt, this thing has a positive solution, because 0 wasn't an option. Let's figure out the number of negative solutions possible. So to do that, we need to compute p of negative x, which maybe I'll do a little bit faster this time. So I put a negative sign inside of an x to the 5th. That negative sign can pull out in front. So I'll get negative x to the 5th minus 7x to the 4th plus, minus 19x cubed minus 47x squared minus 60x minus 46. How many times does the coefficient change sign from positive to negative or negative to positive? 0. So how many negative solutions might there be? 0. There are no negative solutions. Cool. So that's actually interesting. So if you remember last time, there was this subtlety in the rational roots test that, right, the rational roots test gives you this list of rational numbers, but you really need a plus or minus sign in front of all the options. Do we need that plus or minus sign anymore? No, because I know there are no negative solutions. So let's go through the rational roots test and find all the rational roots. So let's see. Applying the rational roots test, if p over q is a solution to this equation, then what does p have to divide? Possibly by flipping back 2 pages in the notes to where the rational roots test is stated. So in general, if you have, if you're applying the rational roots test, which form of the polynomial does p have to divide? The constant form, I think? Happily, that's even like already written on the board too. So, what's the constant form of this polynomial? So p divides evenly into 46. What about q? Yeah, it has to divide the leading coefficient, which is 1. So what are so now, all of the possible rational roots will be a p over a q. What are all the things that divide evenly into 1? 1, like maybe negative 1 if you want to count that, but we don't want to count that, because we know the negative ones won't be valid in this case anyway. What are all of the things that divide evenly into 46? Let's just go through it. Does 1 divide into 36? Yeah, 1 divides into any integer. Does 2 divide into 36? Does 3 divide into 36? Does 4 divide into 36? Yeah, because 36 is 4 times. Does 5 divide into 36? 6? And in fact, 6 is the square root of 46, so that's like a flipping point. So we've really found all of the solutions. So all of the possible rational roots are 1, 2, 3, 4, 6. And now let's count up. So 46 is 4 times. 46 is 3 times. 36 is 2 times. 36 is 1 times. And there are all of the possible rational roots. So is that like 9 numbers that we might have to plug in? So on the one hand, like we've seen that it's not so hard to just ask a machine to evaluate a polynomial at 9 inputs. But I think we can get some good intuition by just looking at a graph to find the things that are even maybe valid to check.
So we don't have to figure out anything for q because it's all just going to be divided by 1.
Yeah. So, right, x is p over 1, which is just p.
Okay.
Yeah. So, I mean, maybe those need a 1 in the denominator, but what does division by 1 do?
Right.
It doesn't do anything.
But if it were to be a bigger number, then.
Yeah, if q could be like 1 or 2, then you would have twice as many options. Well, you would have more options than that because you would have all of those divided by 2. So let's try to decide if any of these are solutions. And let's do it by plotting first. Let's plot x to the 5th minus 7x to the 4th plus 19x cubed minus 37x squared plus 60x minus 36. Did I actually type in the polynomial correctly? Okay. And I mean, Wolfram Alpha defaults to some plot. And there's the plot it's giving us. So this suggests that there's a root close to 1 and a root close to 3. It doesn't tell us with absolute certainty that there's a root at 1 or a root at 3. A graph can only tell you approximate information. But it definitely tells me that I don't need to bother checking for a root at 2. And maybe just to be more confident, let's, because there were more options, there were things beyond 3. So let's plot this from x equals 3 to, I don't know, let's go out to 12. I know that we're looking for things farther than that, but I think this will give us enough information. So does it look like there could possibly be a root at 6? No. At 9? At 12? If this pattern continues, any other roots? I guess maybe it looks like there might be a root at all, but there isn't. The one from 0 to 3 basically told us that too. So by graphing, there may be roots at 1 and 3. Do you think that we should double check that those are actually roots? Yeah, let's actually evaluate. Plugging in 1 is like, yeah.
I don't know, like, it says there's 5, 3, or 1, so why are we getting 2 roots?
Aha, so that tells us that tells us that something weird is happening. So Descartes' law of signs returns the number of roots with multiplicity. So one of those roots might be a root with multiplicity. So like x minus 1 squared might be a factor. And Descartes' law of signs would count that twice. So that might happen. There might be irrational roots also. There could be a root at like 1 minus the square root, 1 plus the square root of 3. That could happen. Right, the rational least test wouldn't see that. We wouldn't see that because it's not rational. So, yeah, what that tells you is if those are all of the roots, one of them has to be related. So let's try to keep on working this out. So let's just evaluate. So let's take this polynomial. I don't want to have to keep typing the polynomial. This is just that link that's on the web page. Let's evaluate that where x is equal to 1 or 3. And those of you who have just already done the computations, is there actually a root at 1? Is there actually a root at 3? And indeed there are. And I suppose that in the time that it took me to like say all those words, I could have just done online computations anyway, so that didn't save me time. That's okay. All right, so I know that there's a root at 1 and a root at 3, so that tells me something about factors of this. What do I know for a fact is a factor of this polynomial? X minus 3 is, and so is x minus 1. So I could simplify the polynomial by dividing in x minus 1 and then by dividing in x minus 3. And, right, so this means that there are, I'll write on the board because I'll give you guys two choices for what you want me to do. So there are two mindsets that I could take. I could take x minus 1 and divide it into this polynomial. I don't want to write it to get some quotient, to get some result of division. But then I would know that x minus 3 would have to divide into that top thing. Let's see, this was degree 5, this is degree 4. So then I would know that x minus 3 has to divide into the degree 4 thing to give something that's degree 3. So there's one option. I could do polynomial long division twice with linear divisors each time. Or instead of dividing one at a time, I could just divide in x minus 1 times x minus 3. And then I would only have to do division once with something hurdle. What preferences do you guys have? Would you rather have me do division by a linear thing twice? Division by a quadratic once? I think the quadratics have it, and I did the linear thing in previous lecture, so I'll do the quadratic thing this time. So, let's see. Because x minus 1 and x minus 3 divide in. Oh, yeah. Because x minus 1 and x minus 3 divide into p of x. So does, I want to give myself space, x minus 1 times x minus 3, which is, I guess, x squared minus 4x plus 3. So let's see what happens when we divide that in. Let's divide x squared minus 4x plus 3 into x to the 5th minus 7x to the 4th plus 19x cubed minus 47x squared plus 60x minus 46. And in fact, what I'll do is I'll do the long division by hand, and then I'll have a computer do division, and we'll check that way. So let's see. So it's all about leading terms. What do I need to multiply x squared by to get x to the 5th? X cubed. X cubed. So that means I need to subtract the result of multiplying x cubed by the divisor. So that'll be minus x to the fifth plus 4x to the fourth minus 3x cubed. Everyone with me? Are people okay with why those pluses and minuses are what they are? How many people want me to say some words about why those are pluses and minuses are what they are? Okay, cool. So what do you do when you do long division? Right, you use you get an initial guess, and then you subtract off to figure out how much your guess is off by to get a second guess. And that's what I'm doing right here. So this quantity in red is, or at least it should be, the same thing as negative x cubed times x squared minus 4x plus 14. Because that's what you do when you do the long division algorithm. You write a number up there, then you take that number and you multiply it by whatever number is right there, and you subtract that. But polynomials can have some negative signs in them, like that negative 4x. So then you'll have a double negative, which will become positive. So if I've actually distributed correctly, then this red thing is what it should be. Cool. So let's keep on. Let's do the result of subtraction and see what we get. So x to the fifth minus x to the fifth is 0, which is what we knew it had to be. Negative 7x to the fourth plus x to the fourth leaves me with negative 3x to the fourth. 19x cubed minus 3x cubed leaves me with what? 16x cubed? And now I do it again. So what do I need to multiply x squared by to get negative 3x to the power 4?
Negative 3x squared.
Negative 3x squared. So now I need to subtract the result of multiplying negative 3x squared by x squared minus 4x minus 3. And generally I wouldn't do this, but let's see what that is. Negative 3x squared times x squared minus 4x plus 3. And I guess there's a double negative, so those will cancel. Leave me with 3x to the fourth minus 12x cubed plus 9x squared. So what is going to go down here? What will go down here is 3x to the fourth minus 12x cubed plus 9x squared. And now we do the subtraction and see how we have to revise our guess. 3 minus 3 is 0.
Wouldn't it be plus 12x cubed?
Ah, you're thinking, well, there's a negative sign and the sign should flip. But I've already dealt with the minus sign because I put a minus sign out front before.
That's just because you're multiplying by negative 3x cubed and it's already negative 4x.
Oh, yeah. So if you like, it was because those two negative signs canceled. Yeah, so the thing that would go here would be negative 3x squared times x squared minus 4x plus 3.
Okay.
But I need to subtract it, so there would be another minus
So you
sign.
do that first one first. Then.
Yeah.
Okay.
Mm-hmm. So 0x to the fourth, so that 0 has to be a 0. If it's not, then I screwed up. Plus 4x cubed plus 47 minus 47 plus 9. Let's see, 17 minus 9 is 8 minus 28x squared. All right, so what should the next one in the division be? Yeah, so I need to ask myself how many times does x squared go into 4x cubed? And yeah, the answer is 4x. plus 4x, and now I need to do that same subtraction. So minus 4x cubed plus 16x squared minus 4 times 3 is 12x. People feel okay so far? All right, so what should, well, I have to do the subtraction. 4 minus 4 is 0. Minus 28 plus 16, let's see, 8 minus 6 is 2. 1 minus 12, x squared minus, 60 minus 12, 8. 5 minus 1 is 4, minus 48x plus 48x minus 46. So what should the next term in the resultant division be? Negative 12. And well, on the one hand, like if I believe that this is actually a factor, then what should the remainder after division be? 0. So I know that the remainder has to be 0, but maybe it's worth doing a checksum to see that the remainder is actually 0, because if the remainder isn't 0, that means I screwed up the division. So let's check by actually seeing what it has to be. So let's compute the remainder term. So I'll have plus 12x squared minus 12 times 4 is 48x. That's good. Plus 12 times 3 is 36. Yeah, that's 0. The remainder is 0. Good. So let's see what that means. That means that the polynomial I started with, p of x, is the same thing as x squared minus 4x plus 3 multiplied by the thing in the top, x cubed minus 3x squared plus 4x minus 12. But let's see, so I already know how this factors. That's x minus 1 times x minus 6. So that gives me a solution at 1 and a solution at 3. Is this a degree 2 polynomial at this point? No, it's degree 3. We don't have any good tricks. But one thing we could do is we can check for rational roots. So the only rational root that this thing could possibly have must be a rational root of the original polynomial. What were the only rational roots the original polynomial had? 1 and 3. So let's see if 1 or 3 are roots of that. That will let us run division again. When you plug in x equals 1 to just this piece, do you get 0? When you plug in x equals 3 to that piece, do you get 0? I see some heads nodding. Indeed you do. So here's an observation, so I'll put that in brackets. That's important. So x cubed minus 3x squared plus 4x minus 12 is 0 at x equals 3. So that means it has a factor, right? What factor does it have to have? X minus 3? So let's use that. So let's compute x minus 3. See how it divides into x cubed minus 3x plus 3x squared plus 4x minus 12. And I think that I actually don't want to do it. I think that I've done enough long division on my own for now. Let's have a computer do this long division. Though it may well be that in the time it takes me to manipulate a keyboard with my fingers, I could have solved it by hand. X cubed minus 3x squared plus 4x minus 12 divided by x minus 3 apparently is x squared plus 4. Now are we down to just the degree? Oh, I should. So I just wrote an x squared plus 4 right there. So that tells us everything, yeah.
So when you got to the degree 3, couldn't you just factor it and get the exact same thing?
Okay, yeah, if you just like can see that x minus 3 is a factor, then yeah.
And then, because then the other one is x squared plus 4.
Yeah.
Okay.
And somehow that's exactly what polynomial division does. It tells you how to factor a polynomial, even when you can't just eyeball a factor. But I suppose you could, because you saw, oh, there's like,
By grouping.
I know which things have 3's next to them. Yeah, sure. Anyway, that's like one of those tricks that walks occasionally. So let's write down what we have. So now I have p of x is x squared minus 4x plus 3 times x cubed minus 3x plus 3x squared plus 4x minus 12, which is x minus 3 times x squared plus 4. But I know how this piece factors because I got it by literally multiplying together two things. So x minus 1, x minus 3, x minus 3, x squared plus 4. So there is p of x. And I wanted to set this equal to 0 and solve. Is that now an easy thing to solve? Because you see an x minus 1 factor, one of the solutions is 1. Another solution is 3. Another solution is 3 again. So I guess it's got a solution at 3 of multiplicity 2. And the remaining solutions are imaginary. I guess they're even plus or minus 2i. And that's everything. So this has solutions of x equal to 1, 3 with multiplicity 2, and plus or minus 2i. How do people feel? That seem okay? So, here is what I would like the remainder of today to be. You guys have a page 6 in that note package. I would like you guys in your groups to walk out that final polynomial. Find all of its roots. I would like you to do that while walking with those around you. Discussing ideas. Even like tricks, like if you see how to factor by grouping, then discuss that with each other. And I give each group a single copy of page 6.
If you take this entire thing, make all the answers negative, and then not necessarily
Just put the signs on like the
so negative equation is going to
after you do it, you just find like how many times the signs switch.
plus.
Yeah.
Yeah, the one that I've given you is a single copy. I want one copy from each cluster of tables.
And there are two technically exams for the sign.
Two root?
Yeah.
We just set it to.
Doesn't it also make the first one negative?
No, because it's a cell tower. So negative one, you know what I mean?
Yeah.
Like negative times a negative.
Yeah, 0 to 2.
Oh, yeah.
Maybe I'll interrupt just a little bit. How many people have like computing devices on them? You can use them on yours. You want?
So it's when it equals 0, right? So the one that actually is 0. 3 negative 2.
Oh,
Gesundheit.
Donald thinks since we can have actual divide by x plus or negative. Oh. I think you're right. Actually,